Hi everyone, my name is Lydia and this is what I wish they had taught me about econometrics and introduction. In this video, we're going to continue with proof of the law of iterated expectations, the continuous case. So we're still trying to prove the same exact identity, which we did for the discrete case where we used the sums. Now the sums are going to become integrals in the case of the continuous variables. Before we continue with the proof, we need a bit of a reminder and a few assumptions for the setup. First, we need to assume that x and y are continuous random variables with their joint density, like the PDF, which we're going to say by function x of y, when x and y take particular values x, y here. The actual formula for that is what I have written right here in lighter color. It's just definition for anyone who's taken a statistic course. These are probably things that they had to learn anyways by heart. Side note, we're gonna have to remember the definition of marginal density, which is going to be a direct consequence of the expression that I just highlighted here. Then the conditional density of y given that x has a particular value that it takes. And ultimately, a reminder that the CEF is going to take this shape right here under the continuous case. Okay. So in order for us to show the actual algebraic proof, you have to be aware of this setup and also of all of these formulas right here. The whole purpose of this video is not really to go and check each and every one of those items one by one, but it's just to show you the proof, and we'll just get started with that. So let's start with the definition of the unconditional expectation. So if we had simply the expectation of y, we'd say that's the integral for y there, for a y value here, and then fy in here of y, which would have been basically the equivalent of that probability that we had in the discrete case, dy. Okay. Now, using the law of total probability, we can say that the marginal of y can be written in terms of the joint distribution. So here, using the law of total probability, we can write that f of y for y is equal to the integral, again, of the PDF xy, the joint one, xy dx. Okay. Now, if we substitute this into this expression right here, then our expectation of y is going to be equal to the integral of y over the integral of this expression right here. Okay, sorry about that. Let's do it again. Okay. And we're gonna have to remember the dy as well, which was this bit right here. So don't forget this in the end. It's very easy to forget about that. Keep in mind this dy in here is basically connected to that first integral in here. Now, at this stage in here, you might remember it's very similar to what we did with the discrete case, but we had the summation notation instead of the integral in here there. So if we switch the order of the integration, there is a theorem that you usually use in this kind of proofs, and you say that it's the Fubini's theorem, and that's why you can do it. Again, it's not the purpose of this video to go into that kind of a detail and into that kind of theory, so we're just gonna continue elaborating this. So we're gonna put the integral, so the double integral y then times fxy xy dy dx. And then if we replace the joint density by the conditional times the marginal density. So we're gonna make another side note, so a second side note in here. So what we're going to use is that the joint density, we're gonna express it as the conditional density times the marginal density, which means that mathematically that looks like the f of xy equals to here the conditional f y x y conditional on x times the marginal one, which we defined earlier, f of x for a particular value of x. Okay. Knowing this expression, now we can plug it in the last expression that we achieved, and we can rewrite the whole thing as the expectation of y equals to the double integral of y f of y conditional on x y conditional on x f of x x dy dx. Now keep in mind the inner integral all over again. So we've got this whole bit right here. This is our inner integral. Gives us the conditional expectation, okay? It's just the definition that we had earlier for the CEF. So if we now continue rewriting this, it's literally saying that the expectation of y is equal to the integral of the expectation of y conditional on x. Then we'd have fx x dx, okay? So in a sense, in here, probably would have been a little bit easier to see. So we're kind of gathering this, so to speak. And then the fx dx is still out there. Now, this is exactly the definition that we were looking for. So we have managed to prove that the expectation of y is the expectation of the conditional expectation. Okay, because this bit, so the fact that we applied the integral here, like dx, it means we were trying to apply like some sort of expectation. And then we have inside here the conditional expectation. This concludes basically the algebraic proof, but keep in mind that we are telling in here the same story as we were telling with the discrete case, which means like if we have like each small slice of x, it's going to have its own average y. This is going to give us the, again, the expectation of y conditional on x. Now, if we multiply each slice average by how common that is, meaning by the f of x in here, then integrate it all over x, then the result should be the average of the y, okay? So again, you had the conditional, you multiplied it by the probability, and if you put that all in an integral, you would have gotten the average. So integrate the conditional means, weighted by the marginal density, you get the unconditional mean. And let's write that down so that you can also use this definition to compare it to the discrete case that we talked about in the previous videos, so that you can more easily make that aha connection between the two cases. So in here, we integrate. We don't find the average in terms of like sum over the total number, but we integrate the conditional means weighted by the marginal density. In the discrete case, we said we weight by the number of the observations in a particular like subgroup to get the unconditional mean. Okay. So this proof, once again, shows overall mean is the average of the conditional means. And with this, now we've covered the continuous case as well. In the next videos, we'll continue talking about the CEF, and we'll probably see the law of iterated expectations used in other proofs as well. So I'll see you in the next video.